Hello students, today I am going to discuss periodic trends in chemical properties. This is in continuation with last class. Periodic trends, where here just we should highlight the trends, not the full reaction. Periodic trends in chemical properties. Most of the trends in chemical properties of elements such as diagonal relationship, inert pair effect, effects of lanthanide contraction, etc. will be discussed here, along with discussion of each group of later units. In this section, here actually in this we will focus a study of the periodicity. We will discuss a study of the you can say periodicity of valence state. We will discuss in all. Here first I will try to discuss periodicity trends in chemical properties. Then first properties, you can say periodicity of valence or oxidation states. That I am going to discuss. Periodicity of valence or oxidation states. What is actually valency and oxidation state? You know, in outermost number of electron in outermost orbit, that is called valency and also called oxidation state. Okay, there's a minor differences there in oxidation state and valency. I will tell you later on. Now I am going to discuss periodicity of valence or oxidation states. The valence is the most characteristic property of elements and can be understood in terms of their electronic configuration. Electronic configuration is very, very important, and this valence is the most characteristic property, or oxidation state is the most characteristic property of the element and can be explained, can be understood in terms of their electronic configuration. The valence of representative element is usually equal to the number of electrons in the outermost orbits, or you can tell equal to 8 minus the number of outermost electrons. Correct? Sometimes it will be from the 8 minus the number of outermost electrons. Particularly you can think from period you are going from 1 to 18 electrons. Then metal generally it will show positive means they are losing they have characteristics of losing the electrons. That's why it is shown as a plus. As for example, any metal, sodium, it can lose 1 electron, calcium can lose 2 electron, magnesium can lose again 2 electron, aluminum can lose 3 electron. Then they are positive, then plus 1, plus 2, plus 3. This is called oxidation state. And up to carbon plus 4. This is the middle. After that, what will happen? Electronegative means this character will increase. Means in p orbital, they have tendency to take the electron. Hence, out of you can say total 8, if you will do the minus means for p orbitals, non-metals, and 4 onward, as for example 5, 6, 7, then 5 means they want 3 electron, then it become minus 3. 6 means they require 2 electron, that's why minus 2. 7 they require 1 electron, that is the minus 1. Then this plus and minus, metals will show plus because they have tendency to lose the electron, and non-metal will show minus because they want electron. That's why from the 8, if you want to tell oxidation state, then from the 8 you just do minus of the distance valence electron, particularly for non-metal. Then you will get oxidation state. As for example, 8 minus 3, then 5, 8 minus 4, then 4, 8 minus 6, then 2, 8 minus 7, then 1. Like that way, you will get the oxidation state. Nowadays, the term oxidation state is frequently used for valence. Just I have now already told you, again you consider the 2 oxygen containing compounds. As for example, this is the somewhat difficult example I am giving you. OF2, oxygen difluoride, and sodium oxide, Na2O, that you know, but OF2 it is rare. Then consider the 2 oxygen containing compounds OF2 and Na2O. How just it is, I am giving example to explain the oxidation state. The order of electronegativity of 3 elements, here OF2 and Na2. Then O is one type, F is another type, and sodium again another type. So total 3 types of elements we are considering here. The order of electronegativity of 3 elements involved in these compounds. Then in this compound, fluorine is most electronegative, you know, in whole periodic table. Fluorine is most electronegative element. Then fluorine is greater than oxygen. Oxygen is greater than sodium. Each of the atoms of fluorine with outer electronic configuration 2s square 2p5, 2s square 2p5, this is for fluorine, shares 1 electron with oxygen in the OF2 molecule. Being highest electronegativity, or fluorine has highest electronegativity, being highest electronegative element, fluorine is given oxidation state -1. Correct? This you have to understand. Fluorine is given oxidation state -1. Since there are 2 fluorine atoms in this molecule OF2, oxygen with outer electronic configuration, oxygen configuration is 2s square 2p4, shares 2 electrons with fluorine atoms and thereby exhibits oxidation state +2. This OF2, what is the main characteristics? Oxygen is also electronegative and fluorine is also electronegative. Then here both are an electronegative element, but here just you have to compare which has more electronegative. Then fluorine is most electronegative. Here in comparison, fluorine is more electronegative than oxygen. Then oxygen will behave as a, just like you can say, somewhat positive in comparison to negative. Both are negative, but fluorine is more negative and oxygen is less negative. Hence behavior will be like that. Oxygen is just like a metal, and this fluorine is just like a non-metal. And this behavior means oxygen is showing like a plus character, and fluorine is showing like a negative, already negative character. That's why it is making the compound. Now this other how compound formed, I told you OF2, both are negative, but fluorine is more negative and oxygen is less negative. That its behavior is just like a positive and negative. Oxygen just it is showing like a positive character, and fluorine has a negative character. Now next you can say, since there are two fluorine atoms in this molecule, oxygen with outer electronic configuration 2s square 2p2 shares 2 electrons with fluorine atoms and thereby exhibits oxidation state +2. Then now come to the sodium oxide. In Na2O, it is very clear. Sodium can lose 2 electrons and oxygen can take that 2 electrons, because oxygen lacks 2 electrons. Then in Na2O, oxygen being more electronegative, except 2 electrons, one from each of the 2 sodium. Each sodium will give 1 electron, and oxygen will take that 2 electron. Now this one from each of the 2 sodium, so 2 sodium atom, and thus shows oxidation state -2. Oxygen will show -2, but each oxygen will show +1 oxidation state. This is very clear. Then you can say in other sense you can understand like this. On the other hand, sodium with electronic configuration 3s1 loses 1 electron. Sodium has electronic configuration 3s1. Then 3s1 loses 1 electron to oxygen and is given oxidation state of +1. Thus, the oxidation state of an element in a particular compound can be defined as the charge. Yes, now understand. Thus, the oxidation state of an element in a particular compound, this is related to compound actually. The oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atoms in the molecule. This is the definition. How will you define oxidation state? Then I told you the oxidation state of an element in a particular compound can be defined as the charge as acquired by its atom on the basis of electronegative consideration from the other atoms in the molecule. Now just I am discussing further some periodic trends observed in the valence of elements, particularly hydrides and oxides. In that you will find different oxidation state. It is interesting also. Some periodic trends observed in the valence of elements. That I will tell you, particularly in case of hydrides and oxides. What are that? I will give some examples that you will understand better, and that is examples you will find less actually, but here we are discussing oxidation state, that's why we are giving some examples. First we can say lithium hydride. In group 1, lithium hydride, then lithium has lost 1 electron, then Li plus 1, only 1 plus, then oxidation state is 1. Hydride, you can say lithium hydride, generally hydrogen will lose the electron. It has only 1 electron. When it will lose, then it will form H plus. But here situation is different. Lithium is donating electron. Lithium has 3 electronic configuration, 1s square, 2s1. That s1 electron it is losing. And who is taking this electron? Then hydrogen. Now hydrogen is taking 1 electron. That's why it is H minus. And after taking electron, now its cell is filled. It became 2. Then when hydrogen takes the electron, this is actually less. This happens very less, but when it will take electron, that time it will called hydride ion, H minus. See, lithium became Li 1 plus and H minus 1, means hydrogen also takes electron. It can do both. It can donate electron and it can take electron also. Then when it will take electron, it is called hydride ion. Another example, sodium hydride, same way, Na plus H minus. Other example is KH, potassium hydride, K plus H minus. Now, another example I am giving you from the group 2, calcium hydride. Calcium has lost 2 electron. And hydrogen, CaH, to each hydrogen has taken 1 electron. Then Ca become 2 plus. Oxidation state is plus 2. Hydrogen taken each hydrogen 1. Then become H minus 1. Then here oxidation state of hydrogen is -1. Like that way. Now see this boron hydride, B2S6, BH3, generally BH3 is unstable, then it forms B2S6, boron hydride, and commonly known as boron hydride B2S6. It is a dimer. Dimer means 2. It is a repetition of BH3 2 times, then became B2S6. And here I want to tell you, this boron has what type of a structure? Question is asked in IIT, particularly in advanced level. This is banana type structure. Banana. Just like you have seen the banana, that like a structure it has. This question is asked about its structure, B2S6. Diboron hexahydride, or you can tell dimer of BH3. Dimer B2S6, BH3 into 2. Now, then here you can see BH3, then boron plus 3. And each hydrogen has taken 1 electron, because boron in the last orbit it has 3 electron. It has donated. And who have taken? Hydrogen had taken 3 hydrogen. That's why H minus 1. See the boron has now +3 oxidation state and each hydrogen -1. Like that way, methane CH4 means group 4, you can say CH4. Then C has +4 oxidation state and hydrogen -1, -1, 4. Like that way, silicon hydride SiH4, then silicon has +4. Like that way, germanium GeH4, then germanium has 4 +4 oxidation state. Tin, stannous, what we are telling? Stannous, tin. Sn has also +4. Like that way, come to the these things. Next, 15. Carbon, actually, this third group wise I am talking about. Then now come to the 15th group, NH3. NH3. Then nitrogen has +3. Hydrogen has, each hydrogen -1, -1, -1. Like that way, pH3. P has +3. Arsenic again has 3 plus. Antimony Sb, antimony is also 3 plus. Like that way, H2O, now in water, H2O, H. Now oxygen has taken electron from hydrogen. Oxygen had taken electron from hydrogen. Then oxygen required 2 electron. Then that had 2 hydrogen has given each 1. Then here H has +1, oxygen has -2. Like that way, H2S, S has -2 and H each has +1. And like that way, H2Se, selenium, just like H2O, H2Se is there, selenium Se. Selenium is a poisonous nature. Then now selenium is -2, just like oxygen and sulfur. Selenium also has selenium -2. Don't forget. Question is asked. Now tellurium H2Te. This also has a 2 negative, and this 2 electron is given by hydrogen, 2 hydrogen. Like that way, 17th group, HF, hydrogen fluoride. Fluoride has -1 and electron is given by H. Like that way, it's Cl. Next, chlorine -1, that electron is given by H. Then fluorine, chlorine, bromine, iodine all have taken 1 electron and has -1 state. Okay, like that way, many, you can say, examples are there. I have given a few examples. Okay, there are many elements which exhibit variable valence. Why elements show variable valence? Then its answer is like that. This is particularly characteristics of, particularly I am talking about the d orbitals. These d orbitals have many, or can say many elements are there which exhibit variable valency or oxidation state. This is particularly characteristics of transition elements. Transition elements, 10 electrons are there, no? That's why their oxidation state will be more. Then this variable oxidation state or valency is due to the these things, transition, particularly in case of transition elements and actinoids, which have more, you can say, vacant f orbitals. Due to vacant d orbitals and vacant f orbital, they show more oxidation state. Question is asked. Now I am going to discuss next properties, that is actually anomalous properties. Anomalous properties of second period. of second period. What are that? Just to listen. The first element of each group, the first element of each of the groups 1 and 2, that is the lithium and beryllium. This is the first element of each of the group 1 and 2, the lithium and beryllium. And groups 13 to 17, we are talking about the period. In period, just to go lithium, beryllium, and then 13 to 17, that is the boron to fluorine, differs in many, you can say, respect. This question, very important things I am discussing. These elements in periodic table, starting from lithium, beryllium in S, and then 13 to 17 means boron to fluorine, differs in many respects from the other members of their respective group. As for example, lithium can say unlike other alkali metals, and beryllium, unlike other alkyne earth metals, form compounds. They will form compounds with pronounced, you can say, covalent character. Other members of this group predominantly form ionic compound. This is the different. Beryllium and boron. Beryllium, no, not lithium and beryllium. They form compounds. Lithium and beryllium forms compounds. And covalent compound they form. But other members of these groups, they form ionic compound. This is the difference. Okay. In fact, the behavior of lithium and beryllium, I am talking about the lithium beryllium only, they form organic compound, various organic compound, and other members form ionic compound. The behavior of lithium and beryllium is more similar with second element of the following groups, means magnesium and aluminum. This again important things I am telling you, that lithium and beryllium is more similar with magnesium, properties of magnesium and aluminum. These two elements, lithium and beryllium, has more similarity or is more similar with second element of the group, that is the magnesium and aluminum respectively. And this sort of similarity is commonly known as diagonal relationship. And this question is asked, diagonal relationship. Okay. Then this lithium beryllium has similarity with second element, magnesium, and second element of the group, magnesium and aluminum. Then this similarity is called diagonal relationship in the periodic properties. Okay. Now other things. What are the reasons for the different chemical behavior of first number of a group of elements in the S and P block compared to that of the subsequent member in the same group? This question is important. Again I am repeating. What are the reasons for different chemical behavior of first member of a group of elements in the S and P blocks compared to that of the subsequent members of the same group? Then its answer now I am telling you. The anomalous behavior is attributed to the to their small size. What is the reason for this anomalies? Then anomalies in behavior, then it is given, its reason is given by the small size. Due to the small size, this happens. First things. Other things, large charge and radius ratio. Charge upon radius, this is more. Means charge is more. Large charge upon radius ratio, means charge radius ratio is more. This is the second reason. And third reason, that is the high electronegativity of the elements. Then these three reasons I told you why they differ in chemical properties. Correct? Chemical or physical property also you can tell. This is the main three reasons: small size, large charge upon radius ratio, and third one, high electronegativity of the elements. In addition, the first member of a group has only 4 valence orbitals, 2s and 2p. Now again you can understand that this last this 2s and 2p, for this thing 2s and 2p will come for second I am talking about. 2 means it is talking about the second only. 1s square, 2s square, 2p6. Then this is the, you can say, another reason, that last orbit 2s and 2p orbitals are available for bonding, whereas the second member of the group have 9 valence orbitals. Actually, this you are talking about here beryllium and lithium and beryllium. Then lithium has 3 electrons. Then 1s square, 2s1, means total 3, and beryllium 4, 1s square, 2s square, 4. Correct? And then here, if you will think for the others, then where 3p and 3d are there, then obviously they can make, means I am talking about the elements which have 3p and 3d in the last, then they can make more bond. Their number of orbitals are more. Then as a consequence of this, the maximum covalency of the first member of each group is 4. Boron can only form BF4, boron tetrafluoride, and maximum valence is 4, particularly for boron. Whereas the other elements of the groups, down you come to the group, whereas the other members of the group can expand their valence shell to accommodate more than 4 pairs of elements. BF4 is there, the 4 electron boron has given and 4 electrons fluorine has given. Correct? Then total 8. 8 means 4 pairs. Then the other members of the groups can expand their valence shell to accommodate more than 4 pairs of electrons. Example, aluminum forms aluminum, it can form AlF6, 3 minus. Then here you can see they are forming more than 4. Means here 6, AlF6, 3 minus. Then now they are you can say 6 fluorine is there, 6 fluorine. Then see, now electron pair is more than 4. That's why these are the difference. Why they are differing? Because number of orbitals are more in other elements of the same group. But boron, lithium, there is an exception. There are exceptions because their number of orbitals are less, and number of electrons also are less. But in other elements of the same group, they have more orbitals, more number of orbitals. Means they can have 3s, 3p, 3d, like that. Then they obviously 3s, 3p, 3d means 3s means S is 1 orbital, 3p means 3 orbital, d means 5, 9 orbitals. But in case of 2s and 2p, how much? 2s and 2p means s means 1 and 2p means 3. 3 plus 1, 4. Hence, they can't, I can say, make more bonds. Only 4 pair of electrons. Then their capacity for reaction is different from the other members. Now, furthermore, you can see, just I am going ahead, the first member of p block elements display greater ability to form here pi bond. P pi bond will be, they can form more multiple bonds. The first member of p block elements display greater ability to form p pi multiple bonds to itself. As for example, carbon double bond. One bond is, out of 2 bond, one bond is sigma bond, other bond is pi bond. And you might be knowing that pi bond is due to the, you can say, side-wise overlapping of p orbitals. Side-wise overlapping, due to the side-wise overlapping, pi bond is formed, and sigma bond is formed by, you can say, s electrons. Sigma bond, single electron, one electron from each. Okay, linear, but pi bond is side-wise overlapping. Then here carbon double bond, that is the comes under the multiple bond, and carbon triple bond, N, that is a nitrogen gas, triple bond. Then these are called pi multiple bonds. Then this is the example I have given you. The first member of the p blocks elements displays greater ability to form p pi multiple bonds to itself. Not only that, this can make pi bond with other groups also, like oxygen. Then what are the examples they can make with others? With then carbon and oxygen, they can make pi bond, pi multiple bond. C double bond oxygen, C double bond nitrogen, C triple bond nitrogen. Correct? Nitrogen double bond oxygen means NO. Then they are making pi multiple bonds. Correct? This I told you, this is again different from this particularly I am discussing here that the first member of p block elements, they can form this pi multiple bonds compared to subsequent members of the same group. Now, other things I want to tell you, periodic trends and chemical reactivity. Actually, this periodic trends, some fundamental properties such as atomic and ionic ready, ionization enthalpy, electron gain enthalpy, and valence. This is called fundamental properties. Then this fundamental properties has a relation with reactivity, chemical reactivity. That is called periodic trends and chemical reactivity. Here we are not understanding that property element wise, not trend we are studying here. That's why it is called periodic trends and chemical reactivity. Means this what I told you, fundamental properties such as atomic and ionic ready, ionization enthalpy, electron gain enthalpy, and valency, these are called fundamental properties, and this has a relation with chemical reactivity. That I am going to discuss how they are, these fundamental properties, how they are related to chemical properties. Listen carefully. The atomic and ionic ready, we have discussed actually. The atomic and ionic ready generally decreases in a period from left to right. As a consequence, the ionization enthalpies generally increase. Ionization enthalpy generally increase. Exception is there. Now, after that, this I am talking about in across a period, this happens. And electron gain enthalpy becomes more negative. Electron gain enthalpy becomes more negative across a period, already discussed, because it is very difficult to remove the electron from these elements across a period. Or you can tell, in other words, the ionization enthalpy of the extreme left element in a period is least, and the electron gain enthalpy of the element on the extreme right is highest. Already we have discussed. Now, this highest negative I am talking about. Okay. Now, again you can tell here for noble gases. For noble gases, actually, highest negative is becoming only for noble gases. Already told you, because new orbit will be opened and that will be unstable. Then more negative is for noble gases. Extreme left is the highest negative. That is a noble gases. Having completely filled cells, have you can say rather positive electron gain enthalpy values. Here just simply you understand that noble gases has highest negative value, means more this energy will be released. Now, next we should understand this what I discussed about these things about radius, ionization energy. This what I told. Then what is effect? What is its effect? Then this results into high chemical reactivity at the two extreme and the lowest. Again you listen, these things what I discussed now, this results into high chemical reactivity at the two extreme and the lowest in the center. Middle elements will be least, particularly d orbitals are very, very less reactive. Left and right, that is the most reactive, and middle is the least reactive. Then in the middle d orbitals comes. Then d electrons which have d orbital, they are less reactive. Particularly this transition elements are comes under the middle. First and last means metals and non-metals. Between the metal and non-metals, these are their transition elements. They are less reactive. Then I told you about these properties. These fundamental properties, effect of the fundamental properties, that this result into high chemical reactivity at the two extremes and the lowest in the center. Thus, the maximum chemical reactivity at the extreme left among alkali matter is exhibited by the loss of an electron, leading to the formation of a carbon, and at the extreme right among halogens, shown by the gain of an electron, forming an anion. They are also most reactive. This property can be related with the reducing and oxidizing behavior of the elements. Okay, these fundamental properties, what I discussed, fundamental properties can be related with the reducing and oxidizing behavior of the elements. You know that reducing behavior means elements which have tendency to lose the electron, that is the basic character, and elements which have tendency to take the electron, that is the you can say acidic. Basic character means has tendency to lose the electron, and acidic character means have tendency to gain the electrons. And also reducing and oxidizing behavior means if elements have tendency to lose the electron, that is the called oxidizing property, and elements who have tendency to take the electron, that is called reducing property. Oxidizing properties always means that element have tendency to lose the electron, that is called a process is oxidation. Then this is called oxidizing properties. Some elements have a tendency to take the electron, as for example halogens, then that is called, they have reducing properties. And oxidizing property examples are this group 1 and group 2, S1 and S2, they can lose. Group 1 and group 2 metals, they have tendency to lose, means more oxidizing properties. And P block, they have tendency to gain the electron, hence they have reducing property. This question is asked. Then this I have told that these fundamental properties have relation with oxidizing and reducing behavior of the elements. Now other things, here you can tell this also it is related to metallic and non-metallic character of elements. You already discussed in a period metallic to non-metallic character increases, and in down in group just reverse in group, and in period it start with metallic character in left side and it go to the non-metallic in the right side, but in a group reverse case is there. Okay, and just like in halogen group only, if we will go down, then because of bigger size they can lose the electron. Then losing electron capacity, that is just like a metallic character. Okay, already I have discussed. about the metallic and non-metallic character of elements. Thus, the metallic character of an element which is highest at the extremely left decreases. Extremely left decreases, and you can say non-metallic character increases while moving from left to right across the period. The chemical element of an element can be best shown by its reaction with particularly with oxygen and halogen. Okay, some examples I am giving you just to understand the reaction. Elements on the two extreme of a period easily combine with oxygen to form oxides. Here I want to tell you very clearly in a general way that this left side, I am talking about the alkali and alkaline earth metal. Group 2 is called alkaline earth metal, and group 1 is called alkali metal. Then these metals are, you can say, positive. They are losing they can lose the electron. Then they can lose the electron, means basic character. And this right side, p orbitals, electrons of this p block, I am talking about in general, that these S1, S2 are metal and these are non-metal, p blocks. Hence there will be reaction between metal and non-metal. Always reaction will be fast also. Between metal and non-metal, they react very fast. And why this happens? Because metal has tendency to lose the electron. Metals have tendency to lose the electron, and non-metal has tendency to gain the electron. That's why reaction takes place very fast, and generally they will make, you can say, salt also, or oxide. Example, sodium and oxygen. It forms Na2O, sodium oxide, calcium oxide, magnesium oxide, potassium oxide, rubidium oxide. These are the barium oxide. This I told you. Then this what I told you first, sodium, potassium, calcium, magnesium, rubidium, cesium, all are from the these things, S block element, and all things oxides, fluorine, chlorine, bromine, all are coming from the P block. Then say another example, sodium and chlorine. Sodium is from the S block, chlorine is from the P block. Both are reacting, NaCl is forming. Like that with calcium and fluorine, calcium fluoride, calcium and oxygen, calcium oxide, magnesium and chlorine, magnesium chloride, magnesium fluoride, potassium iodide. See, means one from left side, other from the right side. Means one from this S block, other are from P block. Then this reaction takes place. Okay, this I have told you in a general way. Nitrogen also, this carbon, again I am telling you, some few questions are asked in examination that I am going to discuss. The elements under this I already told you, elements on the two extremes of a period easily combined with oxygen to form oxides. Already I told you. The normal oxide formed by the element on extreme left is the most basic. All things what I am going to discuss now are very, very important for examination. The normal oxide formed by the elements on extreme left, means S block, is the most basic. As for example, sodium oxide, whereas that formed by the element on the extreme right is the most acidic? Question is asked. That example they will give many examples and they will ask which one is acidic, which one is basic. Then if it is from the this S block, means extreme left elements, then that will be basic. And if it is from right side, P block side, then that will be acidic. Now I am telling you, listen carefully. The normal oxide formed by the element on extreme left is the most basic. Example, sodium oxide is basic because sodium is losing the electron, whereas that formed by the element on extreme right is the most acidic. Example, Cl2O7. Here chlorine is losing electron and giving to oxygen. Then this is both are belong to the P block. That's why it is acidic. Cl2O7 both belong to P block. Oxides of elements in the center are amphoteric. Now oxides can be formed by S group also, P groups also. And oxides of elements in the center are called amphoteric. Example, aluminum oxide, arsenic oxide. Generally, these are oxides of elements in the center. Actually, despite arsenic and aluminum both belong to P block, but it is not like you can say halogen. It is somewhat left towards middle. Then these aluminum oxide and arsenic oxide are called amphoteric. Remember it. Aluminum oxide, arsenic oxides are amphoteric. Amphoteric means it have character of both, because it's just like a boundary, that metal is finishing and non-metal is starting. It is coming in that way. That's why it is amphoteric. It has both character, acidic character and basic character. That's why it is called amphoteric. Or sometimes it will form neutral. Neutral means neither acidic nor basic. Neutral means zero. Then neutral example is, keep in mind, very, very important thing, direct question they will ask. Then carbon monoxide, CO, NO, N2O. Nitrous means NO, nitric oxide, N2O, nitrous oxide, carbon monoxide. N2O, it is laughing gas. Only here I am telling you, N2O, nitrous oxide. Then CO, NO, N2O are neutral. Direct question they will ask in many examinations. For UPSC also this question are asking. UPSC and IIT, these questions are asking. Whatever now we discussed, examples of oxide, acidic oxide, basic oxides, neutral oxide, amphoteric oxide, I have discussed. All are very, very important. Don't forget. Amphoteric oxide behave as a acidic with bases and basic with acidic. If a base is there, that time it will show acidic character, and when a base is there, then that time it will show acidic character. This is the characteristics of amphoteric oxide. It behaves as acidic with bases and as a basic with acids, whereas neutral oxides have no acidic, no basic properties. Now I am going to discuss further. Among transition metals, particularly 3D, two series are there, 3D, 4D series. Then among transition metals, the charge in the atomic radii is much smaller as compared to those of representative elements across the period. Representative elements, already told you that P block elements plus S block elements, that is called representative elements. Then these in comparison to transition metals, the charge change, you can tell, change among transition metals, the change in atomic radii is much smaller, as compared to those of representative elements across the period. The change in atomic radii is still smaller among inner transition metals, means 4F. F means lanthanide series we are talking about. This change, atomic radii change, is very less in D block elements, in D series, in comparison to the representative elements. And further, this change in atomic radii is further or still smaller in 4F, means lanthanides and actinides series. The ionization enthalpies are intermediate between those S and P blocks. In these cases, in transition metals, I am talking about, that is series, transition series, maybe transition series or inner transition series, means D and F. The ionization enthalpies are intermediate between those of S and P blocks. Already name I told you that in middle has middle character. We are coming between S and P, hence all character will be between these two blocks. As a consequence, these I am talking about the D and F block elements. As a consequence, they are less electropositive than group and group 2 metals. D block elements, F block elements have less electropositive than first and second metals, means they can lose less, they have tendency to lose less electrons. Okay. Now next I am going to discuss, in a group, the increase in atomic and ionic radii. In a group, the increase in atomic and ionic radii with increase in atomic number generally results in a gradual decrease in ionization energy or ionization enthalpies, and regular decrease with exceptions. Some exceptions are there in third period elements, and a regular decrease in electron gain enthalpies in case of main group elements, means representative elements. Again I am telling you, in a group, the increase in atomic and ionic radii, in a group I am talking about, the increase in atomic and ionic radii with increase in atomic number generally results in a gradual decrease in ionization enthalpies and a regular decrease in electron gain enthalpies in case of main group elements. In main group elements, thus the metallic character increases down the group and non-metallic character decreases. Here already discussed these things. The metallic character increases down the group and non-metallic character, this also decreases. Metallic character increases down the group, this is correct, and non-metallic character also decreases. Metallic character increases, then metallic character increases in a group, then non-metallic character also decreases, because they are becoming more and more metal. Then what about the just reverse, non-metal? Non-metallic character decreases. Metallic character increases, non-metallic character decreases. This trend can be related with their reducing and oxidizing properties. Okay, this I have discussed. In the case of transition elements, however, a reverse trend is observed. This also, if what I discussed in down, metallic character increases and non-metallic character decreases. Then in case of transition metals, reverse case is there. Then their main region is very small size. When you will study lanthanides and actinides series, that time exact region you will understand. Today I am stopping only here, and now I have finished this chapter. Next class I will start with new chapter. Thank you.